Hello and welcome to the logic of it all. In this video, we will look at binary search trees. So what's a binary search tree? If you remember from the previous video, we compared linear search and binary search on sequential data structures like arrays and vectors. And we realized that if the sequence that we are searching in is sorted, then binary search outperforms linear search significantly. So it runs much faster and does the same in doing the same task. So the natural question to ask is, can we do something similar to binary search? Can we get inspired by binary search that we can perform on a sorted sequence of values to do something similar in a binary tree? Because remember, when we talked about using binary trees as a data structure, the problem with doing any type of search, either using pre-order, post-order, or in order, was that in the worst case, you may need to go through all the nodes until you find what you're searching for. So the question is, can we apply some type of idea from similar to binary search in this scenario? And again, if we want to push this analogy a little bit further, then we should say that binary search is applicable on sequences that are sorted. So maybe what we need here is a sorted tree. But then the question is, how do you define a sorted tree? Because in a sequential data structure, it's clear what sorted means. But in a tree, how is that defined? And that's the definition of a binary search tree. So a binary search tree, or sometimes called ordered binary tree, is a binary tree where at every node, all the elements that are on the left subtree of that node are less than the node, and everything on the right side, on the right subtree, are greater than the node itself. And that should be true not just at the root level, but on every node in the tree. If that property holds, then we call the binary tree a binary search tree. Now, if this is a little bit too abstract, let's take a look at an example. So we have three binary trees here. It's easy to see that all of them are binary trees, and the keys stored them are integers in this case. The question is, between A, B, and C, which one of them is a binary search tree? Now, if you look at A, we immediately notice that here we have stored 14 on the left subtree of 10, but the values on the left subtree are supposed to be less than the value at the node itself, and 14 is not less than 10, so because of that, A is not a binary search tree. How about B? How about this tree over here? Now, if you look at 10, everything on the left side of 10, 7, 8, and 9 are less than 10, so everything is fine, and everything on the right side of 10, we have only one value, 12, which is greater than 10, and everything is good. But remember, this property must hold not only at the root, but on every node. So if we focus on 7 now, we see that 8 is stored on the left side of 7, but it's not less than 7. So because of that, B is not a binary search tree either. But if you look at the binary tree in option C, you can verify that everything on the right side of 10, 7, 6, and 9 are less than 10, and everything on the right side is greater than 10. Then if you go and look at 7, everything on the left side, which is only 6, is less than 7, and everything on the right side, which is only 9, is greater than 7. And then 6, 9, and 12, they don't have any children, they don't have any subtrees, so there isn't anything to check, which means that C is actually a binary search tree. Now we can imagine that there will be some confusion if we have repeated keys in a binary search tree, and usually the assumption is that the keys are distinct in a binary search tree, so we don't repeat the same key. And from a practical point of view, also that makes sense, because if you're using these trees as some type of data structure, the key is the identifier for each value. Like for example, if you're imagining this as a data structure for holding records of students at the university, then the student ID is going to be the key, and the student ID is unique for each student. So we don't have repeated keys in our binary search tree. Now, when we define binary search trees as a data structure, then we need to perform operations. So for example, we need to search for elements in a binary search tree, and we also may need to insert new elements into a binary search tree, and also maybe remove some elements, delete some entry from our data structure. Now in this video, we are going to only look at insert and search. Okay, and the point here is that operations that change the binary search tree must preserve the property that defines a binary search tree. So if you're removing an element, you need to do it in a way that after removing that node, the remaining tree is still a binary search tree. And if you are inserting a new node into a binary search tree, you need to do it in a way that after the insertion, the tree is still a binary search tree. So that's the trick here. Now, here we are going to insert a sequence of keys, 10, 7, 13, 15, and so on, into a binary search tree in that order. And the assumption is that at the beginning, the binary search tree is empty. So first we insert 10. So what we are going to end up with is a binary search tree that contains only 10. Now we need to insert 7. Now the way that works is we look at the value on the top, which is 10. Now 7 is less than 10, which means that it needs to go to the left side of 10. The next value to be inserted is 13. We start from the root. 13 is greater than 10, so it has to go to the right side of 10. So that's 13. Okay, and you see that at any stage during this insert operations, the tree that we end up with is a binary search tree. The next element to be inserted is 15. So we start from the root. 15 is greater than 10, so we go to the right. 15 is also greater than 13, so we go to the right again, and we insert 15. Then we insert 18. Again, 18 is greater than 10, so we go to the right. 18 is greater than 13, we go to the right again. We are here, 18 is greater than 15, so it has to be on the right side of 15. Then the next value is 9. If you compare 9 with the root, 10 is less than 10, so it has to go to the left side. Now the next value is 7. 9 is greater than 7, so it has to go to the right side of 7. So that's where we insert 9. Then we have 27, greater than 10, greater than 13, greater than 15, greater than 18. So 27 goes all the way here. 2 is less than 10, so we go to the left. 2 is also less than 7, so we go to the left again, and that's where we insert 2. And 8 is less than 10, so we go to the left to 7. 8 is greater than 7, so we go to the right to 9. 8 is less than 9, so it has to be stored on the left side of 9. 16 is greater than 10, so we go to the left to 13. 16 is still greater, so we go to the go to the right to 13, and then right again to 15. 16 is greater than 15, so we go to the right again to 18. Now 16 is less than 18, so we go to the left and insert 16 down here. And finally 4 is less than 10, so we go to the left to 7. 4 is still less than 7, so we go to the left again to 2. And 4 is greater than 2, so it should be inserted to the right side of 2. So that's the binary search tree that you get after, which is initially empty, and then you insert this sequence of integers into your binary search tree. Now, For the next operation, searching a binary search tree, let's go back to our phone book example from our previous video when we said that we can use binary trees as some type of data structure where the name is the key and the value is the phone number. Okay, now if we do something like pre-order or post-order or in-order search, we may, depending on which one and depending on which name we are looking for which name we are looking for in the tree, we may need to go through almost all or sometimes all of the nodes until we find what we are looking for. But if you look at the names as the keys here, and also if you think about the order of the names as the alphabetical order, so in that case, Alice, because it starts with A, is less than Bob, and Ian, because it starts with an A, is greater than Bob, because it starts with B, and so on. If you think about this type of less than or greater than, then you see that this is actually a binary search tree, because everything on the left side of John, Bob starts with B, Alice with A, Ian with I, all of them are less than J, and then Mary on the right side, M is greater than J, so Mary is on the right side, and the same with Bob. So this is a binary search tree, and we can use this property to perform a faster search, something similar to binary search in this tree. But again, the condition for this type of search to be applicable is that your tree must be a binary search tree. Okay, and here's how the search works. So we have a value that we are looking for, a key that we are looking for, K, and what we do is we start from the root. So here's the root. So we compare K with the key at the root, and there are three possibilities. It's either that K is exactly the same as the key that we see at the root. In that case, that's our lucky day, and we just return the value there. So if the name that we are looking for is exactly on the top, then we return the phone number and we are done. So that's the first possibility. But it's more likely that they're not equal. So in that case, it's either that K, our key that we are looking for, is less than the key that we find at the root or greater than. If it is less than, then we know that because this is a binary search tree, we know that all the less than values must be on the left side. So what we do is we go to the left and start over. So we go to the left subtree and start over, which means a recursive call. On the other hand, if the key that we are looking for is greater than the key that we find here, let's say the key that we found there is K prime. So if K is the key that we are looking for is greater than K prime, then it must be stored in the right subtree. So what we do that in that case is we go to the right subtree and start the search over. So these are your recursive calls. And we repeat, or we make these recursive calls over and over. So again, if you are here, you compare K with the key that you find here, K double prime maybe, and it's either that they're equal or K is less than or greater than, and we do the same kind of one of these three things and so on. And this is a recursive algorithm, so we need to talk about when we stop. So we stop when either we find what we are looking for, the key, and then in that case we return the value. In the case of phone book, we return the phone number corresponding to that key, to that name. Or it could be that we go down a path in this tree until we reach a node that doesn't have any children, and then we need to go either left or right, and we reach to an empty tree, and that means that the key that we are looking for, or in the case of the phone book, the name that we are looking for, their phone number, does not exist in the phone book, in the data structure, and that means that your search has failed. So these are the base cases for this recursive algorithm. Now, again, to make it more clear, let's go through this example. The key that we are looking for is 6, and this is the binary search tree. I leave it to you to check that this is actually a binary search tree. But what we do is we compare 6 with 7, and 6 is less than 7, so we go to the left. We compare 6 with 4, 6 is greater, so we go to the right. We compare 6 with 5, and 6 is greater, so we go to the right again. And we compare 6 with 6, and we find it here. Now, for simplicity, I only put the keys here, but you can imagine that these numbers 7, 2, 1, 3, and so on, these are the identifiers. So names in the phone book, or maybe the student ID, if this is a data structure for storing student information. And then besides the key, there are other information here corresponding to this key. Like if this is a student, these are the records related to that student, and then we can retrieve them when we find the right node. So that's how binary search works here, and here are the steps in more detail. So we compare our key with the key at the root, which is 7. 6 is less than 7, so we go to the left subtree, and we repeat the same thing. This time 6 is greater than the root key, so we go to the right, and right again, and finally we find the node that has 6 as the key, and that means that the search is finished. Now here's another example, and this is supposed to be 11. So this time we are looking for 9. So again, we start from the root. 9 is greater than 7, so we go right. 9 is less than 11, so we go left. 9 is greater than 8, so we need to go right. But if we try to go right, we reach the empty tree here, which means that the search has failed. And if you look at the entire tree, it should make sense, because 9, the key 9, doesn't occur anywhere in the binary search tree. So it makes sense that the search should fail, actually. And here are the steps in more detail. So first, comparison with the root. 9 is greater than 7, so we go to the right subtree. Then do the same thing. This time 9 is less than the key at the root, which is 11, so we go left. And one more time, the key that we are looking for is 9. The key at the node that we are looking at is 8. Since 9 is greater than 8, we need to go right, but there is no right. The right subtree is empty, and that's another base case for this search algorithm. And in this case, the search terminates, but unsuccessfully, which means that the key that we are looking for does not exist in the binary search tree.